So, welcome student to this introduction to nonlinear optics course. So, this is our third class. So, in the previous two classes we have learned about the Maxwell's equation and the corresponding wave equation and its solution, and we find that its solution is a special kind of solution we call the plane wave solution. It has a specific form. Why it is called the plane wave solution, that is also discussed in the previous classes. Then we find out that there are different kind of media are possible. If the media is isotropic, that means the physical property of the media is same and irrespective of its the direction, then the problem is relatively simpler, because electric field vector E and the displacement vector D are parallel to each other. Also the polarization, which is the dipole moment per unit volume, that is also parallel to the applied electric field. That means, if I apply the electric field in a particular direction, then the polarization will be in the same direction. However, this is not true in anisotropic medium. So, we introduced the anisotropic medium in our last class. So, we continue the concept and learn more about the anisotropic medium in this particular class. So, let us see what we have in this class. So, we have under basic linear optics, still we are in the basic linear optics domain. Today we are going to learn the anisotropic media in more, susceptibility tensor and its properties, and finally how the electromagnetic wave will propagate through an anisotropic medium. So, let us go to the next slide. This is the previous slide. We have already introduced this slide in the last class, but let us do that once again. This is some sort of recap. So, the expression suggests that in the slide that in anisotropic media D and E are not parallel. There is a main issue here. D and E are not parallel, and it is not parallel because of the fact of this susceptibility tensor. This is a susceptibility tensor quantity due to which D and E are not parallel. Now, D is expanded in terms of polarization also, and in this equation we can see that D and E are not parallel because P and E are not parallel. That means, the dipole moment that is generated due to the application of the electric field has different direction that of the electric field. So, if I write the relationship between the polarization component Px, Py, Pz, this Px, Py, Pz is no longer proportional to the Ex component, rather the Ey and Ez component are still there in the system. So, we have a matrix like form, and this relation is very important in nonlinear optics, and we will know in the future classes how these things will leads to some other issues. So, let us go back to the next slide. So, this is also a figure that we have shown, the left hand side figure, that applied electric field and polarization is not in the same direction, they are not collinear, and the reason here is shown in this figure. Here we can see that this matrix, we have some kind of points, these are some kind of points. These points are associated with the corresponding charge. So, what happened that when an electric field is applied, the charge in the entire material, which is bounded by the positive charge of the nucleus, they get shifted from their original position, and if the electric field is vibrating with respect to time, what happened that it also start vibrating. That means, the separation of the charge that also start vibrating. So, now if I consider this vibration as a spring mass system, then this will be the entire matrix. Now, in anisotropic system, what happened that this spring whatever is shown here with the blue and red, they are not in the similar kind of spring. So, the spring constant is different for these two cases. So, what happened that if I launch an electric field and due to which if something is displaced, so this displacement may not be in the same direction of the electric field, rather this displacement is complex. So, this complex displacement cannot be explained by this collinear thing. So, that means the displacement of this charge will be in a different direction and the electric field, applied electric field in maybe in different direction. So, if I now try to understand the x, y, z component of this, then you can see that x, y, z component with respect to E field is already there. So, that means the x component of polarization now depends on the x, y and z component of the electric field, that we have already discussed. So, let us go to the next slide and see what we have here. As I mentioned, once I write the susceptibility tensor in this particular form which is shown here, the relationship between P and E is shown here. So, this leads to this particular arrangement leads to a matrix form, and here we have a susceptibility tensor which is in the matrix form with rank 2. So, P and E are now in vector form, this is a vector form, they are related to some kind of matrix we called is susceptibility tensor. These has some component and this component basically related to the displacement of electric, the displacement due to the launching of electric field. And now these components are here in this particular matrix, 9 components are there, but we know that any matrix can be suitably modified under proper coordinate system. In this case, if my coordinate system is a principal, we called a special coordinate system, we called a principal axis system. So, under principal axis system, we can diagonalize this particular matrix, which may be helpful, because when we diagonalize this system, here we can see that this 9 component now compressed to 3 different components and only the diagonal components are there. And this is a very straightforward technique. If a matrix is given to you and from this matrix you can find out what are the eigenvalues of this given matrix. So, the eigenvalue are the diagonal elements. So, that is one way to understand that I can diagonalize a matrix, and when I diagonalize the matrix, the quantity that is sitting in the diagonal are nothing but the eigenvalues of these things. And if somebody asked how to diagonalize a matrix, that is also well known, that a matrix has some eigenvectors. So, if I use this eigenvector and form another matrix and make a similarity transformation, then because of this similarity transformation, what happened that I can diagonalize the given matrix under that coordinate system, and this coordinate is made by the eigenvectors. So, we can do that, I mean this is not a very big deal, we can do that. So, let us go back to the slides. So, here we can see that after diagonalizing the entire things, so we can write P and E in this particular form. So, P vector can be now represented a relatively simpler form because all the diagonal elements are gone, but still chi xx this component is may not be equal to these components. So, that means if I launch an electric field having same Ex and Ey, forget about Ez component, I launch an electric field and this electric field is distributed x and y. For example, this is the coordinate system, this is my z direction and I launch an electric field here E, and if this angle is 45 degree and if it is a vector E, so I have a component here with E 0 root over of 2 and here E 0 root over of 2. The amplitude of the electric field are same. So, E x and E y are same. So, that means my electric field is well defined, this is around 45 degree. If that is the case, what happened? If I put this into the equation, I can also figure out what is my P x and what is my P y, and if I make P x and P y, if I want to find out the ratio, you will readily find that if I make P x divided by P y, this ratio, it comes out to be chi x x divided by chi y y. Here if I divide the E x E y component, for example, let me erase this part. Yeah. So, E x and E y components was 1. Here as I mentioned, if I do P x and P y, their ratio is chi x x chi y y. So, that means the direction of E and the direction of P is different, because the ratio suggests that their angle between x and y is 45 degree, that means it is oriented along 45 degree in this plane. P x and P y is also, that means the P is also in the same plane, but its orientation is not 45 degree because we have this ratio. It is only true when chi x x and chi y y are same. If chi x s is equal to chi y y, then you can say that P x and P y in the same direction. That means P x and P y ratio is 1, that means E and P in the same direction. But this ratio is normally not same. In anisotropic system, these values chi x x, chi y x, it should be x y, and z z are not same, they are different. Since they are different, the angle between these two are different. Okay. So, the same thing, D matrix can be, D vector can be represented in terms of the susceptibility tensor, and here the susceptibility tensor is written in this form. It has 9 different components as is written, but these 9 different components may not be different, because susceptibility tensor has some kind of symmetry. Here the symmetry is, if they are real quantity, then epsilon I j is equal to epsilon j I. Considering this is a real quantity, in case of complex, the I j is equal to the complex quantity. So, that means they are forming some kind of Hermitian relationship. So, if this susceptibility tensor has this property, so readily we can understand that this 9 component now shrink to 6 different components. So, that means whatever the value I have in the diagonal case, say 1 1, 2 2, 3 3, it is different. Now, 1 2, 1 3, 2 3, these 3 components 1 2, 1 3 and 2 3 is same as here 2 1 and then here E 3 1, E 3 2. So, these 3 components are same, because if I interchange these things, they are same. 1 2 is equal to 2 1, that is why I write 2 1, 1 3 will be equal to 3 1. So, I can also write it is a 1 3. So, these 3 are same. So, that is why I have 6 independent components. Okay, now let us understand why these components, which is epsilon I j is equal to epsilon Gi. Try to understand this in detail. So, one way is to use the energy expression. So, in many places you find that energy density can be represented in this way. If this is the case, so this is some sort of proof that epsilon ij is equal to epsilon Gi. So, they are symmetric in nature. I mean this coefficient are symmetric. So, U is now energy density. So, energy stored per unit volume, this is the energy density, definition of energy density, and I can write this as this way. If I write this, then D is epsilon I, epsilon bar double bar I, or epsilon double bar K, epsilon 0 double bar K E. This is the definition of, this is the relationship between D and E in anisotropic system. So, in component form I can write d I is equal to epsilon I j and then E j. Once I have this, then I can put it here in this equation. So, I put this relationship here. So, if I make the dot product between E and D, it comes out to be the summation of, if I make the dot product E and D, if I make the dot product of that, so the result will be Ex dx, Ey dy, Ez dz. So, if I write in component form, it will be Ei di, I running from say x y z, so 1 to 3. So, E1 d1 plus E2 d2 plus E3 d3, something like that, where E1 d1 are the x component, E2 d2 is the y component, and so on. So, now I can write this in this particular form, this component form, and now I also use the relationship between D and E. So, I have this. So, Ei is there, in place of Di I write epsilon ij Ej. In the similar way, B can be represented at this, but I am not writing any other way B and H, because I am not bothering about this term. This is a magnetic term due to the magnetic effect, but as I mentioned in my last class that we are using this kind of materials where the magnetic effect is not there. Only I am interested in the, I mean, if the system has some electric property, or the dielectric constant is important here. Okay, so I write U in terms of this component form. Once I write this E in this component form, then this is the way one can write. So, then what I try to find out is the power flow in unit volume. Once I say power flow the unit volume, then there is a rate associated with that. So, the rate, when the rate is associated that means I try to find out with respect to time. So, that is why I make a derivative of this U with respect to time. This is the amount of power flow per unit volume, because U is the energy density, so amount of power flow per unit volume. So, when I make these things, make a derivative, so the derivative will be over this quantity and this quantity, because U was half of this Eij stuff. Now, in the second step what we do, that we make a derivative with respect to t, and this quantity has Ei and Ej. Since this quantity has Ei and Ej, we write this derivative into two parts, Ei Ej dt and Ej di dt. This is the two part. We know that if the function is Ei and Ej, then when you make a derivative, if these two functions are multiplied to each other, then one function multiplied the derivative of the other function plus the other function multiplied by the first one, derivative of the first one. So, this is the rule we know. So, using that rule I have these two terms, and the rest of the part is same. I am not, as I mentioned, the magnetic term I should not bother. Okay, so this is the amount of power flow we have when I use the density when I use the energy density of the form half E dot d plus B dot h when I use this form. But there is another way to find out the amount of energy flow per unit volume, and that is through the Poynting vector. So, Poynting vector also we defined in our last class. It is the amount of energy flow per unit time per unit area, or in other words the amount of power flow across unit area. So, the power flow per unit volume, if I want to find out this quantity, which is the same thing that we have derived in terms of U. So, now we are doing the same thing, we try to find out the power flow per unit volume. So, what we will do here, there is a mistake. So, it should be written at can. So, what we will do, we can make a divergence of E. So, that is the power flow into the system. The negative sign suggests that it is the power flow, and this power flow is inside the system. So, into the volume, if the power flow I calculate, I need to do these things. So, unit wise, if you find S is something where the amount of power flow per unit area. So, the watt divided by unit area means the area will put there. So, it is watt divided by area. So, now when we make a divergence of this quantity, that means you are making some kind of operation like del x. X is sitting here, which is a space variable and should have a dimension. It should have a dimension like distance. So, that means length. So, length dimension is here. So, length into area, this will be a dimension of volume. So, eventually what we will have, this quantity give the power flow per unit volume, which is the same thing that we have derived here by using this U. So, now what happened, E can be represented in terms of S can be represented in terms of E and H, and when I write E and H, then I can write this identity, vector identity, in this simple way. Grad dot E cross H can be represented in this way. This is a standard way to represent the grad, we know that. Then what we have? So, in the next slide we have the same expression that we have shown. Now, what we will do, we just replace this and this with our known quantity. That means, this is from Maxwell's equation, I have curl cross E is minus del B del T and curl cross H is del D del T. If I replace these two things, then this equation, because of this replacement from here, I can have a expression which suggests the power flow per unit volume is E dot d d divided by dt H dot dB dt. A dot product again can be represented in terms of summation. So, if I do this dot product in summation form, it should be something like this. Again, the relationship between D and E is used here, because vector, the ith component of the D is represented by ij and then ej. By the way, one thing I should mention here, that this notation is called Einstein notation. When we have a repetitive index, here in this case the repetitive index is j. So, that means there is a summation associated with that. So, sometimes we write this same expression as this way, summation over j epsilon ij and then ej. This equation suggests that the summation is over j, and when the j is repeated, then this summation is over j. So, now Einstein notation suggests that if this repetitive indexes are there, we should not use the summation sign. So, that is why I write d I epsilon I j E j. J is a repetitive index. So, that is why the summation is not required, the summation sign is not required. However, here I put the summation sign to make understand that over which the summation is, because dot product itself has a summation over I and this d has a summation over j. So, that is why there are I j sitting here. In the similar way, h and b is there, but there is no j. So, only one summation is there and that is over I. Now, if I put these two things together, then I have a relationship du dt and these things S minus of divergence of S and have a form like this. So, du dt, if you remember, du dt, this particular form we have already derived in our previous slides. So, now if I compare, which I will do in the next slide, if I compare these two things, then I will have the same expression, but two different forms. So, this is the comparison between two expression. This is coming from this Poynting vector and this term is coming by using the u. So, these two things are eventually the same thing, but we have two different equations. Now, we put this equation side by side. When I put this equation side by side, I find that this term and this term will be cancelled out, because this is the same term we have both the side. Then we have interesting expression in our hand, and this interesting expression suggests that half of epsilon I j E I d I d j dt E j d I dt is equal to this quantity. Now, this equation will be consistent only when epsilon I j will be equal to epsilon j I. So, if you try to understand this, you need to make a summation over that. When you make a summation over that, then there are two summation here I j. So, epsilon I j will be epsilon I and j. So, I will take some value j and j will take some value I. So, if I say these are the same thing, then we will have a term that is twice. So, that things will cancel out this half term, and because of the cancel out of this half term, eventually we will get a single equation like this. So, this equation will be consistent only when epsilon I j is equal to epsilon j I. So, with this treatment we can prove that this is the case here. Okay, so go back to our anisotropic system. So, under principal axis system, this is our expression of d and e. Epsilon can be represented in terms of k like this also, kx, ky, kz, and if the system is isotropic, we know that epsilon ii, epsilon xx, epsilon yy and epsilon zz are same. If epsilon xx and epsilon yy are same, but epsilon zz are not same, this belongs to the anisotropic system, and we call this anisotropic uniaxial system. In the similar way, if all the three terms are different, it is called the anisotropic biaxial system. So, uniaxial, biaxial and isotropic system. In isotropic system, all the terms are same, but here in other case it is different. So, now what happened, if I write kx, ky, kz, I can find that kx is nothing but the refractive index of x, y and z, which are different. So, that means the refractive index along x, y and z direction is different for anisotropic system. It is a very important outcome. The refractive index of x, y and z are different. Now, if I put y, y and z, z same as x, x, then we find that in isotropic system the refractive index is same in all the three directions. So, in anisotropic system the refractive index is different for three different directions. Okay, now finally we like to understand how the wave is propagating in anisotropic medium. That is a very important thing, because it is not trivial. Some things are not trivial. So, let us start with our electric and magnetic field vectors, which is these two, and then I use the Maxwell's equation, and from this Maxwell's equation I can find one expression that k cross E is equal to H. this expression, this is not a new expression, this expression we have already figured out in the earlier classes. So, k cross E means the H vector is perpendicular to k and E, that is the outcome, that is the first outcome, that H vector, that means magnetic field vector, is perpendicular to the vector k and the vector E. Next expression what we have is this. This expression is coming directly from the Maxwell's equation, that is fourth Maxwell's equation, and this equation suggests that D vector again perpendicular to the vector k and H. Previously we find that H vector is perpendicular to k and E, now we find that the D vector is perpendicular to k and H. Another equation, this is the first Maxwell's equation we have. So, from this Maxwell's equation we have a very important outcome k and D. So, k and D are related to k dot D equal to 0, that means k and D are perpendicular. So, we have k perpendicular to D. So, k vector is perpendicular to D. So, few informations we have. So, now I find out what is the significance, what are the significances of this expression. So, there are 4 expressions written here, This 4 expression suggest, first expression suggests D vector is not parallel to E, this is the first conclusion. That means, if I have a D in this figure, if I look, if I have a vector D, so E will be in different direction. So, this is the direction of D and this is the direction of E, that is the first conclusion we have. Second thing is that k dot D is 0, that means k vector should be perpendicular to the D vector. If that is the case, D vector is given. So, the k vector should be perpendicular. So, this is 90 degree, this is 90 degree. Another expression is here, which is S and E. This expression suggests that S vector is perpendicular to E and H. Before considering this S, let us consider the fourth expression, and this fourth expression suggests that H vector is perpendicular to k and E both. So, now k and E in this plane, so H vector has to be the perpendicular to this plane. So, here we find that H vector is perpendicular to this particular plane. Once H vector is perpendicular to the plane, it is also perpendicular to D, it is also perpendicular to S, that is for sure. Now, S vector is perpendicular to E and H both, that means S vector and E vector are perpendicular. So, I can write here this is 90 degree. So, one thing very interesting we figure out here is that k vector and S vector are now not in the same direction. So, k vector is not parallel to S vector, and in the previous case we find that the S vector is something which gives us the direction of the energy flow, and in isotropic system we find that the energy flow is the same direction of the k. That is why in the previous class we put this k vector inside this intensity term. So, that means the energy is flowing in the same direction of the k, but that is only true when the system is isotropic. In anisotropic system we find that there is a difference, the direction is different with k and S. So, k is a flow of the field, but the energy is flowing completely different direction, and there is a difference phi. This phi is an angle, and we call this angle as a Walkoff angle. So, we will learn more about Walkoff angle in our future classes. So, here we like to conclude today's class. So, today's class we will learn few interesting concepts, that susceptibility, what is the susceptibility tensor and how I diagonalize this susceptibility tensor, and these diagonal elements are nothing but the refractive index along x, y and z direction. And then also we figure out that how the electric field vector and the displacement vector and S, that means the Poynting vector, and the k vector are related to each other in an anisotropic system. And we find a very important thing that the k vector and the energy flow s vector are not in same direction. So, the wave is propagating along one direction and the corresponding energy can flow in a different direction, and there is a gap between these two, angle between these two, and this angle is called the Markov angle. We will learn more about this, we will do more rigorous calculation to figure out how these things is going on in our next class. So, with this note, so let me conclude here. Thank you very much for your attention. To see you in the next class. Thank you.